Let's think about elastic materials and the very important relationship between stress and strain. Now you remember that stress is PSI, force over area. And you remember that strain is the ratio between the deformation and the original length. It's how stretchy the thing is. Elasticity, when something is elastic, it means you put a load on it and it stretches or compresses, but then when you take the load off, it goes back to its original size and shape. And we should note this: all materials are elastic. Stone, concrete, steel, window glass, whatever it is, every material in the world is elastic. And what that means is that every material in the world will deform when you put a load on it, and then after you remove the load, it will return to its original size and shape, as long as you don't exceed its limit, whatever its limit is. And of course, glass is going to have a different limit than steel. There's this relationship between how much stress and how much strain, and it's a very important property of materials. It's called Hooke's law. Robert Hooke was a mathematician, and Hooke's law says stress is proportional to strain in elastic materials. Well, every single material on the planet is elastic, so Hooke's law applies to every material. Stress is proportional to strain, and every material is elastic. Let's think about a couple of imaginary examples to work our way into this. So here's a platform with there's a gauge up here that can measure how much this thing deforms, and we put 100 pounds on it, it stretches some. Double the amount, 200 pounds, it stretches twice as much. Put another weight on, 300 pounds, triple the load, it's triple the deformation. But this is an elastic bar, so when we take the load off, boing, it springs back to where it was. And if we made a graph of this thing with 100 pounds, 200 pounds, 300 pounds on the vertical axis, and how much it elongated on the horizontal axis, and we plotted those points, how much did it stretch, we'd see, oh, we've got a straight line there. Here's another example. Let's say we have a 1x1 square bar, and we'll put it in a tensile tester, and we'll put a load of 5,000 pounds on it. So how much is the stress, by the way? Force of 5,000 pounds, area of 1 square inch, so we must have a stress of 5,000 psi. And the bar lengthens some amount or other. Then we double the load, which means we double the stress. Now it's 10,000 psi, and the bar lengthens twice as much, and so on and so forth. Again, if we plotted those points, we'd see the graph of how much stress versus how much it strained would be a straight line. And we'd also see when we took the load off, when we stopped pulling on this thing, this bar, being elastic, would spring back to its original length. So Hooke's law says stress is proportional to strain, and that means that this graph of stress versus strain is a straight line. And that ratio of stress to strain is the slope of that line. You remember when you were in algebra class and they were talking about graphing a line? They had that formula y equals mx plus b. That was the formula for a straight line. What was m? M was the slope of that line, wasn't it? So m, the slope of that line, is just how much it changes in the x direction over how much it changes in the y direction. In other words, stress over strain, it's a constant in this straight line, and whatever that ratio is for this particular material, That's the slope of that line, and it's a constant number all the way up. Well, things can't go on like this forever. Depending on what material you're using, things will stop going on. Let's say you're doing mild steel, and it happens that for mild steel, when you reach 36,000 psi of stretch, something weird is going to happen to that bar. All of a sudden, it's going to keep stretching even though you don't apply any more stress to it or any more load to it. And once it starts doing that, when you take the load off, it's no longer elastic and it's not going to snap back to its original length. You have reached the proportional limit, where stress and strain are no longer proportional, and after this the graph stops being a straight line and starts doing funny things. Here is a stress-strain diagram for mild steel out of our book. And so there are three little points that are really close together here in the graph, and don't worry too much about what the different ones mean. It's not that important to us. But so you have reached the elastic limit, so this thing is no longer going to spring back when you take the load off, and the material now is not elastic, it's plastic. Plastic is like, have you ever played with silly putty, where it's a toy, it's kind of a stretchy clay thing, and with silly putty, it's designed not to be elastic, and when you stretch it, it stays stretched. That is called plastic behavior. That point where that happens is the yield point. Your steel has yielded, and now your graph turns almost horizontal. Even if you do not increase the load or the stress, you're just, okay, hands off, I'm not touching you. That bar is going to keep on stretching, stretching, stretching. More and more strain. It's in the plastic range. Up to that yield point, the graph is a straight line, and that material is elastic. When you take the load off, it will spring back. Beyond the yield point, the material is no longer elastic. It starts exhibiting plastic behavior, and you'll see a big increase in strain. It'll keep stretching, even with no increase in the stress. So now I'm talking about these three dots that are close together on the graph, and we're not going to worry about it too much. But so that was the yield point. Just beyond that is the plastic behavior, and the material is deforming permanently. To be precise, the point where stress and strain are no longer in proportion is called the proportional limit, and now the graph is no longer a straight line. The point at which the material is no longer elastic is called the elastic limit, and above that point is where the material has yielded. It's turning plastic, and that's called the yield point. And really, we just think about the yield point. That's what's important to us. What is important about this? So it's no longer elastic. It's now plastic. The material has yielded. For all practical purposes, that material has failed. Now, it didn't break, did it? It has not broken into two pieces. It has just stopped being elastic, and it's all stretched out like silly putty, and it's not coming back. The point where it actually breaks is called the ultimate stress, and that is the point on the graph where the graph goes up here to a high point. See that? It says ultimate stress. That's where it actually breaks. But we don't care too much about that when we're designing things, because especially in materials like wood and steel, what matters to us is where is the yield point. Here is a table out of our book. Average strength values for certain materials. So notice that these two sets of columns are yield stress, so that's where the material stops being elastic and it turns plastic, that's where it yields. And over here is ultimate strength, that's where it breaks. And let's look at mild steel. The ASTM number for mild steel is A36. And notice up here in the top of these columns, it says that these numbers are in KSI. What does that mean? K stands for 1,000, doesn't it? So this is not 36 PSI, this is 36,000 PSI, or 36 KSI. And what this is telling us is that the yield point for mild steel is 36,000 PSI, and notice this, tension and compression are the same. And then it says the ultimate stress for mild steel is 58,000 PSI. So you could put 36,000 PSI of stress on the steel. Under that, it's still going to be elastic. Above that, it's going to yield and go plastic. If you keep going and you give it 58,000 PSI, the thing will actually break in two. Now notice concrete down here at the bottom. Remember how I think we put concrete into test cylinders and then we send it to the lab and try and break it. And notice for concrete, we don't think about yield stress, we go straight to ultimate stress, and where is the stress point at which it breaks in compression. And the reason for that is that concrete is a brittle material. Steel is a ductile material. Ductile means this material will give you a warning of impending failure. That is, it's about to fail. It gives you warning by yielding. It stretches. It turns plastic. When you see steel stretching, you say, oh my gosh, this is very bad, I must get out of here. It gives you warning. Brittle material, like dry spaghetti or concrete, does not give you warning of impending failure. It goes straight to ultimate stress without measurable plastic deformation first. But for materials like steel, as long as you stress it within the elastic limit, like this piece of metal in a press brake, within the elastic limit, when you take the load off, it springs back, no permanent deformation. If you exceed the elastic limit, like this bent nail, then the deformation is permanent. And we can use this to do things like forming metal. Here's a finger brake for sheet metal and a press brake for thicker steel plate. These are in the welding shop at LCC. Or we can use this, exceeding the yield point, to make things like paper clips. And you've probably done this with a piece of wire sometime. You bend it so far that you can't straighten it again. So just to review quickly, here's our stress-strain diagram. In the elastic range, stress and strain are proportional. This graph is a straight line, and the material is still elastic. In the plastic range, it keeps straining, keeps stretching with no increase in load, and the material is no longer elastic, it is now plastic. And once the material has yielded and gone into the plastic range, it will not come back. And for all practical purposes, that material has failed.